Awesome, guys. It's 4 o'clock and we have some more joining us. Sven, Woo-sung, welcome to the call, guys. And yeah, we're going to be diving a little bit into Float's tech stack. So it's quite a broad topic, and it's going to be quite difficult to sort of summarize every piece of tech that we use, but I've sort of broken it up into categories, and we're going to demo things a little bit. And if you have any questions as you're going, just throw them in the Q&A. I'll read it as we go and I can answer. So feel free to throw those in. Yeah, let's start. So my name's Jono Prest. I'm a software dev from Cape Town, South Africa, and this is my home that I'm sitting in right now. I'm a coder, I love music, and I love outdoor things. You always find me trail running and hiking and surfing and stuff on the weekends if I get the chance. So yeah, that's me. Today, we are going to be talking about the Float tech stack. So I've broken it up broadly into 3 categories here. We've got, and this is sort of like a general Web3 tech stack as well. So you've got your contracts, your backend, and your front end. And I see Greg put his hand up. If you have a question, Greg, why don't you just pop it in the Q&A? I will answer as we go. Cool. So the way we're gonna do this today is I've built a little mini protocol that uses all these components. So I can show you them quite simplified as we go, and hopefully each of these components will make sense. Some of these are very simple, or some of them are very rudimentary to Web3 tech. So if you are a developer in Web3, you might find this some of these concepts to be very rudimentary. Some of them are going to be maybe new to you. There might be some interesting tools here. So yeah, feel free to, if you're watching this in retrospect, feel free to skip around to the different sections of the video. But we'll be going through these one at a time and I'll demo them as we go. So I've created a little protocol called the HODL wallet, and I'll explain how that works as we go, and hopefully it'll make sense and it will tie these pieces of tech together as we go. So let's start with the contract section. Contracts are obviously where like the tech happens on Web3 protocols. This is where the magic happens essentially. So we develop our smart contracts in a language called Solidity, and we use Foundry in our toolchain. So let's just start by chatting about what is Solidity. So a lot of you might be familiar with this topic already, but Solidity is an object-oriented high-level language for implementing smart contracts. And smart contracts are just programs, applications that run on the blockchain, and they govern the behavior of the way we interact with the blockchain with accounts. Okay, so what does it look like? It's a curly brace language like C++ and JavaScript. So if you're familiar with something like that, it will probably look kind of similar to it'll look familiar to you. It's statically typed, which is an important point, and it compiles to ABI and bytecode. So those are the 2 things that you need to be able to compile Solidity to. Bytecode is what we run on the blockchain. So that's what we'll actually deploy to the blockchain and what runs on the blockchain. And the ABI that it compiles to is what we can use in our dApps, in any sort of any sort of application or server that we're creating. We would use the ABI to enter that kind of gives us a shape of a contract that we can interact with. It tells us what functions we can call and stuff like that. The bytecode is the raw code that runs in the blockchain. Okay, so let me just quickly say hi. How's it, everybody? Jason, Floatin, Z. Still don't know how do you say your name, and Crypto Comical. Welcome, everybody. Cool. Okay, so I've got this little protocol that I'm going to demo to you. I'm going to open this folder called, I'm using VS Code here, and I'm going to open this folder called contracts. Let me just first show you what a Solidity file looks like. It ends with the .sol um, suffix. So you'll find anything .sol is a Solidity file. This is kind of what it looks like. You define the version of the Solidity compiler at the top. You can make imports from other contracts and other packages at the top, and then you will define a contract, right? So a contract is very much, if you're familiar with any other kind of object-oriented language, it's very much like a class or an object. You can inherit. It's got a constructor. It's got all those features of a class essentially. So in this contract, we run a constructor that we define the lockup time. So in other words, this could be like a 30-day savings account or something. So I would define this when I create the contract, I would set the lockup time to 30 days. Now I'm going to skip down to look at these yellow things here. Those are called functions. And these are what you can ultimately call to the block, make calls to on the blockchain. And only when they're defined as public can we actually just make calls to them from addresses and from other contracts and stuff. So in this contract, we can deposit a token. We'll take one of our any token, ERC20 tokens, and we define how much, and we transfer it to this contract. So and then what we do is we set the value that we store these values in a mapping over here, which means we can sort of look up the values we have later per user and per token. So each user will have an index of tokens that they have deposited into this contract. So what we'll do is we set the amount there, and then we emit something called an event here. And that this essentially is a way for us to cheaply look up later what happened with all these, what happened when someone interacted with this function. If we had to store every single time someone clicks here, and we actually had to try and store that in this contract, it would make gas prices really expensive. So rather, we try and emit things in events that make the smart contracts a bit more gas optimized and more efficient. We also have this function called withdraw tokens. So I can immediately deposit something, and it sets, you can see the shape of this thing called a struct over here. It sets the amount that I've deposited and the timestamp at which I deposited it, which we get from the block. So the block.timestamp. Now, when I try and withdraw the token, it's going to first check, it's going to do a require statement, and it's going to check that I've deposited enough of that token, and I have more equal to or greater than or equal to the amount that I'm requesting to withdraw. Otherwise, I'm going to revert with an error called insufficient balance. I'm also checking here that the current time is greater than the current time minus the timestamp that I set is greater than the lockup time. So in other words, I'm checking that we are past the lockup period. And then otherwise I would revert with the error too soon to withdraw your funds. If that is all Gucci, we head on and we transfer the token using this ERC20 interface that we get from the Open Zeppelin packages. And then we just go ahead and reset that value in storage of the user tokens, and then emitting an event one more time. Okay, so that's a quick high-level overview of how this contract works. It's essentially a lockup contract where anybody can store their tokens for X amount of time and not be able to withdraw it for X amount of time. So it's like a savings account, like a bank account. Cool. Okay. So that's just a quick overview of how these things work. No questions yet. Hey, thanks, John, for the re-entrancy. So I'm gonna yeah, we'll talk a little bit about testing later. But yeah, there's lots of things to watch out for here, and this is certainly not necessarily a like I don't know. It's not a bulletproof contract. It hasn't been tested fully yet. So it's great to have eyes on that. Cool. Okay, so moving on, we're going to look at this tool called Foundry. And so now that I've written my Solidity code, I need to try and compile it into bytecode and ABIs like we were talking about. And there's a whole bunch of other things I would like to do. Like I would like to know that my functions work. I would like to know, I would like to get it onto the blockchain and all those sorts of things. So let's go here. So Foundry is a smart contract development toolchain that gives us three tools. One is called Forge, which is what I'm going to be demoing a lot of today. I'm actually not going to demo the other two, but we'll talk about all three. So Forge, Anvil, and Cast are the three tools we get from Foundry. So Forge manages your dependencies. It allows us to install like Open Zeppelin contracts and stuff so that we can get those ERC20 interfaces. And it compiles our project. So it will compile that ABI and bytecode. It runs tests, it deploys contracts, gives us gas reports, and it lets you interact with the chain via scripts. Cool, so that's Forge, and this is like the bulk of the Foundry tool chain that we use. It also comes with a tool called Anvil, which allows you to run a local test node. For those of you that are familiar with other tools like Ganache, it's just like Ganache. Yeah, it allows you to run your simulations off chain, and you can use it for testing your contracts from front ends or interacting over RPC. So that's a nice way to do local development with smart contracts. And then Cast is just a CLI for performing RPC calls. So you can make your contract calls from the command line. You can send transactions and retrieve chain data all from your terminal. Cool. Okay. So let's quickly take a look at some of these tools now. So the way you would get started with a project is you would open up a terminal. Well, you would first need to go to the book.getfoundry.sh and start following their installation instructions. So you can install Foundry. Then what you would do is you would run, I'm not going to do it now because I've already set it up, but you would run forge init, which initiates your project, and it will install the Forge standard library, and it will give you this foundry.toml file. So you'll see what it does is it gives you these three, in fact, four directories: your library, your lib, which is where it installs the modules to. It gives you a script folder, a source folder, and a test folder. So the source folder is where I'm dropping in these contracts. Well, I've got this this HODL wallet over here, and then I've got a little this is just a wrapper around an ERC20 that essentially is just mints and approves immediately, so we don't have to do all of that. Okay, so if I want to build this, I run the command forge build, and it's going to go ahead and try and compile it. So you can see I've already compiled this, so it's finished running. So this is a really nice fast compiler. It's built with Rust, so it runs super fast. Let me just give you another variable here. Just to try and compile this. So if I run Forge build again, you can see how fast it compiles, and it's done. A nice little feature here is you can add the watch flag forge builds -w, and now it will listen for file changes. So as I change, I don't have to constantly run a compiler. It just compiles for me, which is super nice about Forge. Sweet. Okay, so that's building and compiling. Let's quickly chat about testing. So one thing that's super nice about Forge, as opposed to something like Hard Hat, is that you can write everything in Solidity. So let's take a look at this test file that we're going to just use as an example. The way this works is you would inherit Forge's standard library test contract into your test into your specific test contract that you want to run. Then when you define a public function called setup, the setup function will run before every test that you write. Okay, so you would define a setup function, and that's going to run every time before your tests. Then if you want to run, if you want to create a test, it can be a unit test or a fuzz test, and I'll explain that just now. You just have to prefix your a public function with the word test. So every time I use the word test and then I declare the rest of the name, suddenly I've got a little test function, and this is going to be run in the test runner. Okay, let's start by, I'm just going to comment out this withdraw over here. So just a little example of a test is that I'm setting up a HODL wallet that's got a 30-day lockup period. Then I'm using this function called change prank, meaning Forge is now acting as this address. So the message.sender that comes in your contract is from this whatever address you define in your prank. So I've just created a dummy address called address1, and I'm changing prank to user1. Okay, then I'm deploying this instant approval ERC20. As I said, this is just a dummy ERC20 that immediately mints some tokens for me for this user1, and immediately approves the contract for spending it, so that I just don't have to do that later. Cool. All right, let's go ahead and look at this test deposit. This is essentially a unit test. So what we're doing is we're using the skip function, and what that does is it like sets the block timestamp. So we are now at block timestamp 0, and as user1, because that's the prank I'm currently on, I call deposit token on this contract. I'm passing in my cool token, and I am depositing 200 of that token. Then we can go and do some things, like we can run some checks. So I can call the balance of this contract, and I'm expecting that it's going to be 200 now because we've just deposited that in. One other cool function that you get from Forge, from the Forge standard library, is this console and console2, which has a log method on it that allows you to just log things as you go when you run tests. So it's really nice for debugging and just quickly checking what values are coming out. So if I want to run this test, I'm going to start by just commenting. Let's just comment these things out over here. I would run Forge. Let me save that. I would run Forge test, and that should pass. Ran one test and it passed. I wasn't testing for anything. All that it's going to do is check that it's not reverting really at all. Now I can call this assert equal function, assert EQ. That comes from the test library that Forge gives us. And I'm wanting to assert that the contract balance is 200. So I'm being very specific here. So if I run that again, let's have a look. Cool, it's passing. So, and just show you, so you can see that that works. If I were to put in an incorrect value, it should fail now. Yeah, so there we go. It's failing because it didn't pass that assertion. Cool. What I've then done is I've just made a couple more assertions here. I've looked at the specific user tokens and that are in the storage of the smart contract, and I'm asserting that we have 200 as an amount, and that the timestamp was the current block.timestamp because we haven't moved yet. So yeah, that's just an example of how you can do some unit tests. You can test whatever values you want. So one of the really cool things about Forge is that you can do something called fuzz testing, which means I can pass in a parameter to one of these test functions, and Forge will go and try and run this test function multiple times, passing in random values as this parameter. So when it fuzz tests, it doesn't just run this once, it runs it hundreds of times, depending on how many fuzz tests you've actually set it up to run with, which you can define in your foundry.toml. I've actually defined 1,000 over here, which is probably more than you need for development. So what I'm doing here is I'm running the test deposit so that we immediately make a deposit. Then I'm using this other call. We get this object from the test library called VM, which comes with a bunch of methods. And one of the methods is assume, which means that we can sort of guide the fuzzer. We can tell it what options it actually can't use. So what I'm saying here is that the timestamp is going to need to be greater than or equal to 30 days, right? And because this is going to fail if it's less than 30 days. And I'm wanting to assert that this is going to pass. Okay. So, but I want to fuzz on all those values from 30 days upwards. Then I skip to the timestamp. So whatever the timestamp comes through, I skip to that in the block, and then we try and withdraw the token. We try and withdraw 100 of the cool token. So let's see if I run this, what's going to happen. Okay, so it passed. I want to just try and run forge test again. So we got a failure now. As you can see, it chose a different set of random values on the second run, and this time it failed. So this is a really nice way to go ahead and to actually catch edge cases in your code, because you can sort of fuzz on values that you wouldn't have thought of as breaking before. So, and if I want to figure out a little bit more about that, let's just read what John has said. So he said, test deposit will run all the assertions and checks in the test deposit again when called from test withdraw function. Nice. Do you think we should call the other tests from tests, or rather just the same logic? I think you can set it. For me, I don't think it matters too much. It's a little bit cleaner in a way to set up a function that's like if I have to write all this logic out again over here, I don't know. It depends if you want to test different values. I think it's nice and clean to sort of create tests that are also can be modularized as helper functions later on. So I like that, but I suppose it's up to preference. Cool. So moving ahead. Okay, so what I can do here is when I run test, I can also define how what level of verbosity I want in the logs that come back. So if I run forge test and then I flag v, that's the default, is one level of verbosity. Then we could have two levels of verbosity, which will include our logs. So now we should see the log of 200 there in the failed response. If I do 3 levels of verbosity, I'll now get a stack trace whenever there's a failure. Okay, so now I've got a stack trace. I can actually walk through all the things that were called, all the sort of actions that happened, and I can use that to help debug. And if I wanted to do 4 levels of verbosity, that'll run a stack trace across every passing and failing test. So 3 levels is a nice way to go for debugging. Just for the brevity of, for time brevity, the little bug that I left in here is that we actually want this to also be able to equal the lockup time. And so every time it was hitting 30 on that fuzzer, it was actually saying that it was before that time, but it could be that time as well. So that's like, it's a silly example, but it's kind of like what a fuzzer can help you catch. So if I run forge test again, now that I've correctly set this to be greater than or equal to lockup time, it should be passing every time. So we've got our forge test passing, which is great. Okay, cool. I'm going to go quite quickly over the rest of Foundry, because just in the interest of time. So one other really cool aspect, or let me just quickly talk about the gas snapshot. You can run forge snapshots to generate this snapshot. And then if you're wanting to try and figure out if you're going to create something that has a negative impact on gas, for instance, I could, just as a dummy test, I'm going to say, I'm going to define a test bool, a Boolean value over here. And when, oh, sorry, this is the wrong file. Let's go to the HODL wallet. I'm just going to define a test value above this function. So this is in the contract storage. And as we call this function, I'm also going to set that to something. So let's set that to true, just as an example of something that would impact gas. Now, if I run forge snapshots with flag diff, it's going to check that against my previous gas reports and explain how it negatively impacts gas and what kind of percentages you get. So that's quite a cool way of just testing as you go to see if what changes and refactors you make have a positive or negative effect on gas. Cool. Let's see what Jason has to say. Cool. So he says, little tip, you can set in Forge how many fuzz runs you want to. By default, it only does 256, but try catch more edge cases, you can increase the number and leave it running for a long time. Yeah, exactly. So like Jason says, it does 256 by default, but you should be able to define your fuzz runs here in your foundry.toml. I see it actually did go, let's have a look. Maybe I did this wrong. Yeah, so it did 256. Maybe it's not actually supposed to be an underscore. Let's have a look there. We can Google this later, but yeah, I'm not entirely sure. We can Google that later, but I know that you're absolutely right, Jason. You can set the fuzz runs to a different value. And then you can catch way more edge cases. You could leave it running for as long as you want to just keep keep pounding your tests with different values and try and fuzz on them. So that's the power of fuzzing, and it really helps with catching edge cases. So another cool thing that Forge gives us is the ability to write deploy scripts in Solidity, which is amazing because usually you have to write these elaborate JavaScript or something files that sort of chain promises together and get addresses from each other and have to essentially deploy something to read the next address before it can action the next one. So in Solidity, it's so beautiful because as you create this new, like this, for example, this run script here, I create this this new who said that? MJ Foundry fuzz runs. Sorry, I'm getting distracted here, but we can give it a quick try. So he was saying that if we define Foundry fuzz runs equals 1,000, we should be able to change that. Let's see. No, that's the incorrect command, Mike. But there is definitely a way. You can just Google it, and we can figure it out another time. I'm going to keep moving through here with the scripts. Okay, so inside us, if you're importing this script library, it gives us a couple of things we can use. So when you define the function run in your script, this is actually what the script runs when you use the forge script command. Okay, so, and like I said, we get this VM object that has a start broadcast and a stop broadcast method. And it has a whole bunch of methods, but start broadcast and stop broadcast is used for when you want to suddenly activate, essentially switch to using an on-chain, like to actually doing this, broadcasting this to the chain or to the network. So, but what's beautiful about this is that we get the address straight back when we cast address around our instantiation of this contract. Then suddenly I can pass that address straight into my token that I'm deploying. So I'm deploying 2 contracts here. I can log things. I could even run tests between deploying. So I could start and stop broadcasts, run tests on it before I go on to the next before I actually go on to the next deployment thing. So that it's super nice being able to do this with Solidity. And there's a whole bunch of ways a whole bunch of flags you can add to this, but let me go to Forge script. Okay, I'll just walk through this command with you because this was already on my clipboard here. But you can add and remove any of these flags that you want. So I'm inserting my private key. So I've stored this in an environment variable. You could write that straight out there, but I'd recommend using environment variables. I'm passing in an RPC URL that I want it to go to. Again, that's in an environment variable. And then I use the flag broadcast, which means I want to deploy it. There's also a flag there that I'm using called verify, which is another cool thing that the scripts do for us. They automatically verify contracts given if you have an API key for Etherscan. So as it deploys, it goes through and verifies everything. And it's super quick because it has all the addresses essentially, and it knows everything. It simulates this deployment before it actually deploys it. So sometimes all the deployments can end up in the same, getting mined in the same block because it can put them through as one transaction essentially. Or I'm not sure if it's one transaction. I'll have to double check that. But just as an example, we're running the script over here, and it does a simulation run. It logs the addresses that it's going to use. It gives us an estimate. So if I didn't use the broadcast flag, it would have ended over there. But because I used the broadcast flag, it goes on and it starts executing these transactions using my own private key that I've put in my environment variable. Cool. So once it's finished, it gives us the hash, and we can actually go and look at this. Let's go have a look. So this should be the contract address for our HODL wallet. I'm going to go to, I deployed this on Fuji, which is Avalanche's testnet. Cool. Here we got our contract. And if I click on contract, it's already verified. We've got all the code here. HODL wallet. I can read and write. It's got the ABIs for us to interact with. So I can read user tokens. I can write, I can call these methods here. I can deposit tokens, and that's that. So Foundry has made it super easy to deploy, verify everything in one go, which is super nice and super cool. And it's also fast and effortless, and it keeps you writing in Solidity across your whole sort of smart contract framework. Which is really cool. And it's also just so fast with the Rust compiler. Cool. Right. I see Jason says there are separate transactions unless your deployment specifies one. Right. Okay. That answers that question. So there are separate transactions. And yeah, John says deploying in JS is always a nightmare. This is so cool. So yeah, I've also had that experience. It feels like it takes forever. You can sometimes run these, if you have like 30 contracts that have to be deployed in succession, sometimes like deploying with hard hat or something can take an hour while you're waiting for one transaction after the next to be complete. Cool. Okay, let's move on. We've spent quite a bit of time on the smart contracts. I'm going to sort of move quite quickly through the next section. Let's go to, okay. So we've just covered contracts and how we use Foundry with Solidity to develop our contracts. Then let's talk about the backend. So I'm going to just very briefly talk about Hasura because it's a very small part of our system and I don't want to go too deeply onto it. But Hasura is a really cool tool. And I'm just going to quickly spin it up over here. So just going to go into this Hasura directory. And I'm just going to run it in Docker. So that is running. And then there's a CLI that Hasura gives you. And it should, and it allows us to interact with the console. All right, I have to say admin secret. This is just a dummy thing that I haven't set up yet. You can put that in environment variables and that sort of thing. Okay, let me give you a quick show and tell of this. Cool. So what Hasura does is it gives you a nice way to link with a GraphQL server to a database. Let me quickly go back to my slide. I'm going to skip ahead to Hasura. Yeah. So Hasura gives you instant GraphQL and REST APIs on new and existing data sources. So the first thing it does is it sets up a GraphQL server for you. It gives you a nice console to interact with and sort of make edits to your database. You don't have to do it in specific SQL queries and that sort of thing. And it allows us to plug other APIs and services into our Hasura server. And it sort of forms part of our GraphQL schema using something called Hasura Actions. So that's what it really does for us. I'll give you a quick demo of what it looks like. So, I haven't even set up a database here. I'm not going to even bother doing that right now. But essentially, you would connect up a Postgres database, and then it gives you a nice GraphQL Explorer where you can sort of take any tables. It looks at the tables and relationships in your like say a Postgres database, and it maps out a schema that you don't even have to write any SQL commands or queries. You can essentially just talk in GraphQL and have pretty much all the control that you would have with SQL queries. So you can be quite specific about how you want to query things. And it's very quick, easy, and simple to set up. So we use this for some of our custom backend stuff. But yeah, it's not a huge part of our infrastructure. It will become a bigger part of our infrastructure as we move over to Float Arctic, but more on that another time. Cool. So let's talk about a big part of the infrastructure, which is the graph. So the graph is an indexing protocol for organizing blockchain data and making it easily accessible with GraphQL. So essentially, it indexes events that get emitted from our smart contracts. And it gives you what I was talking about, a GraphQL server, which is a nice and easy way to query from like a front end or from any other kind of application for sort of more rich data that we would need. So the graph gives us a CLI that uses CodeGen to map entities from events. I'm going to explain this a little bit more in detail now. It gives you a nice public place to deploy your server, so it's public and it's easily available. So it's easily available for anybody who wants to use it. It's not just for like our particular app. It's actually public, so anybody can go and query our graphs. And it continuously syncs with the blockchain, so it stays up to date and yeah, so you can essentially, it's like almost like getting a live data feed from the blockchain with a nice GraphQL server, as opposed to having to talk to like RPC endpoints to sort of get data from the blockchain. Cool. Okay, let's look at this a little bit. So the first thing is just to quickly go back to the contracts folder. We talked a little bit about how we emit events on smart contracts. So we've got a deposit and a withdraw event on this contract. And that gives us data, the amount, the timestamp, the user, and the token. And we emit this every single time somebody does a deposit or a withdrawal. This doesn't get stored in like contract storage here, because that would be quite an expensive thing to do. It just gets emitted, and then we can capture that using a tool like the graph and sort of create a database that we can query from that. So I'm just going to quickly walk you over a little what the code looks like for the graph. So you would use the graph CLI to, let me go into the graph. So usually, I'm not going to run it now because I've already done so, but you would use, I think the command is graph init. So you would basically create a new graph. And then it would give you a whole bunch of these folders. And the one thing that you have to do is you would define these things called entities in your schema.graphql. So this, what I've done here is I've created 3 entities, a hodler, so this is the user, and it's got their ID and ETH address. It's got, and it stores an array of these token types, which is an entity in itself. And it stores an array of transaction types. Okay, so this is a nice way of getting a sort of a one-to-many relationship. And yeah, so these are things that we'll be able to query nice and easily later on. Cool. So essentially, we want to be able to store every transaction that's happened. And then we also want to be able to sort of manipulate users' tokens. So let's say they have a specific token. As a withdrawal or a deposit comes in, we want to be able to update the value of that token, not just store a new transaction. So that's what the graph helps us do. So I've created these entities. Then in our subgraph.yaml file, I'll define those entities over here. Just sort of flag them. Then the graph gives us a tool called CodeGen, and I'll run it, but it hasn't changed anything. Essentially, that will go into this generated folder, and for all the contracts and entities that you've created, it gives you a bunch of these types that you can use from TypeScript. Then all you really need to do is go and edit your source. Here I've got this hodl wallet.typescript file. And here is where I create some handlers. So this means every time a deposit event comes in, it's going to call this function handle deposit. And I can now manipulate it. So I can say, I want to load up a transaction, either if there was a transaction there that had the same ID. So we either load it up. If not, we're going to create a new transaction with this ID. We set the type, the amount, the timestamp, and we set which hodler and token that is, and then we save it. Then we also we also look at the token. We either load that up or we create a new one. We set the address, the amount, and the hodler, and then we increment the amount because we're depositing to that. And then we save that entity. And the same thing with the hodler. We load them up. If they don't exist, we create a new one. We set their address and then we save that entity. So every time one of these events comes in, it sort of trickles down these handlers and aggregates. And then to deploy this, I would just run graph deploy to the hosted service that I've got. And where that ends up is on the graph website like this. So now I've got a nice GraphQL playground. And I didn't quite touch on what GraphQL was for those who don't know, but essentially it's a query language that allows us to define from the client. So from the side that we're making the call, we can define exactly what we want the data to look like when it comes back. So rather than just sending out a request and getting any data like on a REST API, you would just get whatever shape the data is, and then I would have to manipulate it on this side. I can define exactly how I want the data to look before it comes back to me. Okay, so yeah, I'm just going to use the example query. I have all these like sort of filter options. I can say order direction, ascending. I can say I want the first 3 transactions, and I want to get the hodler and ID, the amount, the transaction type. And now when I make this query, it looks at the server and it gives me all this data back. So now it's given me my transactions. It should have 3 in this array. 1, 2, and 3. So I get all these data types back. I get all the pieces of data that I've defined here. So in other words, if I get rid of this, I don't care about who it was. I'm going to get rid of that. And now it doesn't give me the hodler parameter anymore. So that's essentially what GraphQL does for us. And this is all happening. This is all essentially being synced from the blockchain. So you can see it says syncing 99.9% right now. And the graph is constantly crawling through blocks and just looking for these events that we've defined. If it catches one, it sends it to our handler and indexes it as we've asked it to, essentially. And we've got a database and a server to query it from. Cool. So that's essentially what the graph looks like and what it does. And this allows us to get all the data we need for a front end. It also allows us to make some rich queries that you wouldn't be able to do just from the blockchain. If I wanted to get all these transactions, I would sort of have to query them one at a time from the blockchain, or it just would be a very clunky process, let's say. So the graph makes getting like rich sort of shaped data queries really, really simple and really nice. One issue is that it does run a little bit like it has a time period where it's syncing. So sometimes there can be delays where if there's a lot of blocks to catch up and it falls a little bit behind, especially when like chains have these peak like times where there's gas fees are high and people are transferring making transactions really at a high rate and stuff. So there's a little bit of a problem there. And also another side note is that there's a side project that Float has been working on called the Graph Uncrashable, which will be released at some point in the near future, which is a super cool open source service that allows you to create, that basically helps you with some code gen to ensure that your graph never crashes. And I'll let someone else talk a bit more about that in a Share Friday one day. But that's essentially what the graph does for us. Cool. So John is asking, how does the graph and Hasura fit together? Both use GraphQL and involve data storage and querying. Yeah, so they're essentially our two services that we use as backends that we query on the front end. And on the front end, when you're making these queries, you use a service, not a service, a piece of software called Apollo. And that allows you to sort of create a client that communicates these GraphQL queries. So we essentially can have multiple GraphQL clients, some for graph, some for our prices, some for our Hasura backend, some for various graphs. We can switch between those. And yeah, so we can make queries all within the sort of context of Apollo, as we'll talk about a little bit later with the dApp. Cool. All right, so let's go on. Now that we've talked a bit about the graph and how that works, let's skip to the last part, which is the front end. So this is kind of like where this all comes together and we can get a usable protocol for users. Right, so I'm going to skip ahead. So this is a really interesting piece of tech that that very few people are using. And I think it's amazing. And I was so stoked to learn about it when I joined the team at Float. So Rescript is a language that compiles to JavaScript, and it's a functional language. So it's very similar to like OCaml or Haskell or that sort of thing, but it compiles straight to JavaScript. It's completely type safe. It's very strict with its typing. It's got a formatter that's uniform. You can't configure it, so everybody's code looks very uniform, and it's really nice to code on larger projects with. And it gives you all that sort of like the way that functional programming works really makes complex problems a lot simpler to solve later on down the line. So I would say it's similar to TypeScript, but it's not TypeScript tries to be like a superset of JavaScript. So it always has to catch up with JavaScript updates and stuff. And you also have to annotate types everywhere with TypeScript. So you have to say what type it is. Whereas Rescript is it's a subset of JavaScript. So it only uses a small portion of JavaScript, and it does it really simply and really well. And the typing is inferred. So you automatically get type safety and 100% type safety. It can't make it won't allow you to compile if it's not sure of a type. So you have it's 100% type safe, and that's what makes it so production ready, which is awesome. Cool. So yeah, let me just see what I've written here. So it's simple and super performant. The compiler is written in Rust, so again, it's super fast. There's also really cool libraries and integrations you can use with it that use OCaml preprocessors. So they are sort of things that can run over, that can sort of like add on to the ecosystem and process things like, for instance, Rescript doesn't automatically give you type safety in GraphQL queries, but we can add on a preprocessor that looks through your GraphQL queries, gives them all types, and checks that it matches your GraphQL schema. And if not, it'll throw errors if you write incorrect GraphQL queries. And then if you try and if you try and if you try and use an incorrect data type from a query that you've got, it will also throw errors at you. So it's really it's strict, but it's really fast, and it's really nice to code in. So let me show you what that looks like. I've got this folder here called our DApp. So let's take a look at a component here. So to get this started, I'm going to go to my terminal here. I'm going to go into the DApp folder, and I'm going to run npx. I'm going to start up the compiler, rescript build, and I'm going to add a file watcher there with a W so that if something changes, cool, it's already compiled everything. If I go to, I'm going to go to this component here called user transactions. And this is, in fact, let's go to our hooks. So it gives you a really nice way to do pattern matching, which is like a very OCaml type thing. But it makes things run super cleanly. So for instance, I've defined this type called a GraphQL response. This is similar to how we do it in our actual front end. It's got a loading variant, a graph error variant, which takes a string, and a response variant, which could take anything, but it will have to be defined at some point. It takes this parameter that we pass it in. So I'm setting up a query here. I'm grabbing my GraphQL query, and using Apollo, we pattern matching on this query over here. So sometimes the object comes back with a data field, and sometimes it comes back with an error field. And what we are pattern matching on here is we're looking to see if we actually have if defined data within this within this query. If not, it's going to just show loading. It's going to return this loading variant. If it does have data, it's going to what's the word? It's destructured transactions from it. And then add transactions as a response over here. So essentially, we're simplifying the query structure here just to get the simple variant response here, which is really nice. Now in this component, we call that function use get transactions, and now we can just switch and pattern match on this. So we've got a response type. I could also pattern match on loading over here and return some sort of React component here. I'll just quickly do that. So it says loading. And you can see it threw an error because I haven't handled a case, which is if it's loading, and not if it's loading, if there's an error. So this is what's so nice about Rescript, is it sort of warns you if you haven't handled certain cases. So the error has got a message type, and I'm going to pop in the message over here. So if there's an error, it will just display the error. Sorry, I got that wrong. It's called a graph error. Cool. And now it's happy. It's compiled. So it's so nice because it immediately tells you if you're missing something, if you're missing a pattern. And that's what's really nice about Rescript. Now you can see as it's compiling, it's taking the .res file and it compiles it into this .bs.js file. So it turns it into JavaScript here for us, which can just interop with regular JavaScript libraries. It can run in the browser, it can run in Node. So essentially, it takes our completely safe Rescript, which we can write in a nice functional way, and it turns it into a JavaScript file that can then be, can have complete sort of web compatibility, which is what's so nice about Rescript. Okay, so we're using Rescript here. Let's quickly talk about Tailwind. So I'm going to be very quick about this because we're running over time here. So Tailwind, thanks guys. Sorry, I'm just reading the comments here. Denim has given me a nice compliment saying that I'm explaining things nicely. Really appreciate that. Thank you. And there's a lot of jokes going on. That's great. I'm not going to read all of those right now. Cool. So Tailwind CSS. Let's jump in right there. So Tailwind CSS is a framework, a CSS framework and library. Essentially, what that means, CSS is how we would usually style web system, like we would style web pages. If I open up my developer tools here and I look at the styles, this is all the CSS here. So I can just add in random things like background should be red. And there we go. I've styled the page. I've added in some CSS. But this writing CSS like this can be quite clunky. Like it takes it, and it also separates. It sort of separates you from writing the components nice and easily. So what Tailwind does is it gives you a whole bunch of predefined CSS classes. And when I use class name in all these components, I just write these Tailwind classes. So for instance, instead of having to go and define the border radiuses of with specific pixel values and each corner of this sort of box over here, I can just say rounded XL, and that's going to give me an extra large rounding on all the corners. Instead of defining the box shadow with like the 4 parameters that you need, it just gives you a couple of different shadows, and there's commands for different shadows, but the basic shadow you just call shadow. For padding, like padding inside a box. So what I'm just going to quickly do is I'm going to just spin this up, and so you can actually physically see it. Let me go into the DApp. Let's just run npx next dev. I'll talk a little bit about next just before we go. But if I go to localhost 3000, this is running locally. So here's my little DApp over here. So did you see as I ran that, we saw that loading over there. So that was returning the graph's loading parameter, and that's how we pattern matched for that. Cool. So with Tailwind CSS, you can see these nice round borders, and the padding is sort of this width, this little distance between the edge of the box and this table in here. So if I change that to padding 10, that uses the 10, that's just Tailwind's predefined sort of levels of padding. So it just gives you sort of an abstracted way to deal with this rather than having to define pixel values of absolutely everything. It's super quick. I can say, okay, I actually only want padding on the x-axis, meaning left and right, not up and down. Now I've only got padding on the sides. I could say, I actually only want padding on the left, PL10. So it gives you these really quick little commands, essentially, that you can add into your code and allow you to style things, which makes developing these components really flexible and easy. Another thing about it, which I prefer over something like Bootstrap, is that it's completely tree shakeable. So it gives you this massive library to use, but by the time you build your code, it strips away any of the classes that you're not currently using in your code. So whereas Bootstrap or something, you would load it up and you would have this entire massive 9,000 line CSS file that gets added to your code. But with Tailwind, it strips away anything that you don't use. So you have a really tight package that you ship with in the end. It's also unopinionated. It's not, sorry, let me go back. It doesn't, it's not, you don't have to, it doesn't give you specific colors. Like you don't just say button danger and suddenly you have one style for a red button. It gives you all these little styles that you can sort of formulate your own type of button if you want to. Okay. Yes, and it's also the other really cool thing is it's easy to do sort of queries and stuff. So like, for instance, I could say, I want the background only if we have a medium sized display. I'm going to say MD column. I'm going to say BG red 400, which is the color they give us. And now, because my display is over medium, it gives me that red background. But if I make it smaller, below medium, suddenly I don't have that red background. So very quick way to do media queries and other things like, well, let me bring that option back, but maybe something like hover as a command. And now as I hover, it gives me that red style. So it's a very quick and easy way to do like media queries and make things really responsive. Sweet. Okay, cool. Last things about the UI. Let's have a dig. So React and Next.js. So this is kind of the guts and the framework we use for developing the dApp. So React, it's a declarative component-based UI framework library for JavaScript. So what that means is I don't write, let's say I wanted to change the text on a button as I click it. I don't specifically write that the command to go to the website and change the text. I can just update a variable in JavaScript and the browser reads that from state, as we call it, and essentially renders it for us. So we don't have to write imperatively, as you call it, when you don't have a framework like React. You can just write you write components based on state and it just updates things for you, which is really nice. It's component based, so we can quickly look at what that means. So for instance, if I go to this action form over here, instead of, I can reuse this component input that I've created, which is defined in this file over here. And here you can see how much code is written in one input and all the styling and the label, but I've simplified it down to the single component input, which I can then pull right in here to my form and just define the label, the value, and the function that we want it to do. So that's what using components, that's why it's valuable using components, is like you can really abstract things. So as I read this code, I can just see, okay, that's an input. Okay, that's a button. That's a radio input. It doesn't have to be so cluttered. And this form doesn't have to be, 100 lines long, where I sort of get lost where I'm at. It's really easy and composable to read, and it's reusable. So now I don't have to accidentally, another developer might come onto this and not know exactly what styles to use for the inputs. But because we've already styled an input component, they don't have to worry about like making sure they've got all these styles in their inputs. They can just import the input components and it's already styled exactly the same. So that's sort of why it's so modular to use React. Cool. So the other thing about React is that it's a single page application. So that means it's just giving you one HTML page and it sends you a bunch of JavaScript, and then the JavaScript is what sort of paints the page for you, and it changes the page, it fetches data. And so everything gets shipped in one page, and then and then from the client, as it hits the client, that's when it starts loading into a page and making requests and stuff like that. So that's what a React is. It uses a single page application sort of style. And one more thing to note is that like traditional web development has three sort of files that it works with. It has JavaScript, which is like your code logic. It has HTML, which are the components that you see on a page. It's like the actual images and text and inputs. That's your HTML. The CSS is the styling. It's how do we make it look pretty and stuff. So traditionally, those are written in separate files, and to be able to see what styles a specific component is using, you would have to switch to a styling file and look for the class that it's using and stuff like that. What JSX, which is the language that comes with React, does for you is it sort of pulls these three files into one little component. So inside this, let me go back to the input components. We have our HTML, we have our styling, we have our code logic, and that's all sort of housed within one component. So it's nice, it's modular, and it sort of allows you to understand from a logic, styling, and like a component-based perspective all at once what's happening within a component. And this is the crux of it, is that it makes scaling things a lot easier. So it makes it really easy for someone to jump into your code base and sort of use a component that you've made. They don't have to spend days and weeks learning how you've decided to write your code logic, because it sort of follows an order. It's encapsulated into these little components. It's really easy to sort of collaborate with. So that's really, in my opinion, the biggest reason to use React is how scalable it is and easy it is to write large scale applications with other developers. Okay, and lastly, let's just quickly chat about Next.js, which is a framework for React that essentially allows us to write React pages on a server before it gets sent to you. So traditionally, a React, like I said, is a single page application. It sends you a blank document with a whole bunch of JavaScript that then goes and paints your document and makes all the calls and stuff for you. Whereas what Next.js is, it allows you to, on the server, before it gets to your computer, before it gets to your browser, it allows you to sort of render and create that web page, as well as make any sort of API calls, load in data. It can do that from the server before it even gets to you. So by the time it gets to you, you already have a page that's built. And then it still has all the sort of functionality of React, where you can do it from the single page, but it allows things to happen really fast and package things into much smaller sizes, because I don't need to send you an entire application in one network request. I can just send you what you're requesting at a time. So maybe you're just requesting one page. I can just send you that page and the logic that's needed for that page. So it's much simpler. It's much faster. It loads faster. That's what's like the benefit of using Next.js. So it also has built-in routing, and you can just write regular React inside it. It just sort of manages all the server-side stuff almost by itself and gives you a couple of extra tools to work with. So yeah, that's what we're using there. So maybe we can give you just one last little tour of this dApp. So here is a dApp that's interacting with this contract. So I've set this up to be a 60-second wait period. So I should be able to deposit, I'm going to deposit, let's say 9 cool tokens. And this is opening up my MetaMask, which I'm going to confirm the transaction. And we can see it going through, deposit token over there. Just going to let that go through. Cool, it's deposited. So I should have 9 more tokens over here. Now, these are queries coming from the graph. If I actually, just while we're in this 1 minute waiting period, I'm going to try and withdraw it, and let's see what happens. Oops, errors. lots more to do on this still, clearly. I'm going to just try and withdraw 10. And let's see what happens. Don't know why that's actually happening. I'm just going to do a hard refresh. If this doesn't work, it's all right. Sorry, guys, I literally built this morning, so it hasn't been tested at all. Cool. So we're trying to withdraw. I don't know if that was under a minute, but if it is, it should actually fail. Let's see if it does that. It should say that we're under the lockup time. But it may have passed a minute now. It's past a minute, so we managed to actually get that. Cool. So anyways, we can deposit and withdraw from this application. Have a look at how I can write these GraphQL queries. And what Rescript does for me, let's say I'm looking for transaction type over here. Oopsie. I'm going to try and put that in, and let's see what Rescript does with the compiler here. I'm going to save that. Whoops, it says unknown field transaction type on hodler. So again, Rescript is just awesome with catching those kinds of bugs when you make incorrect queries. So this is the query I'm making to get tokens and balances. And then I've created some hooks that use Apollo client that I was talking about earlier, and runs the query and either returns the data or an error message or this loading sign. So if I go to user transactions, it goes and tries to load up these transactions. If it gets a response, it's going to give us this nice HTML table, and it's going to map out the transaction type, the amount, and the hodler ID. And this should be up to date with the graph. So as fast as the graph is, so should this table be. Let's see if our transactions are in there. Cool. So there's actually, I can't even remember what we did. Okay, so our balance is currently 61. Let's do one more test here. So if I deposit 4, I should have a balance of 65. And we can see the graph doing its thing. So we'll have to check that that goes through. It's going to run speed up. Cool, that's gone through. Now this should, when I refresh, depending on how fast or slow the graph is, move to 65. There we go. So the graph has gone and indexed that for us. And yeah, that's what makes this, that's what makes using like the graph and GraphQL with React and stuff such a nice composable framework to use. Cool, guys. I know it's been a really long Share Friday. I hope that was interesting to you. And yeah, shout if there's any questions. I haven't seen any questions yet. Maybe I should just double check the Discord chat. If you're struggling to ask questions in the in Zoom, just head over to crew chat and I'm going to be looking over there. Cool. Thanks, Crypto Comical Shot, for listening through. Hope you found something useful in there. Cool. Thanks, Christina. Awesome, John. Hope everyone's having a Power Friday and enjoys the weekend. And yeah, let's get building. And yeah, if anybody is interested to do a little bit more of a deep dive in any of these specific tools, you're welcome to like sort of post on the chat, and we could maybe organize another Share Friday that sort of does a more specific deep dive into one of these tools, because I know this was sort of like super high level overview. Denim, I haven't made the repo public, but I'll certainly do that. And then we can host it on our floats organization if you want, and we can send out links and stuff so people can take a look. And I'm also happy to compile some links to all the docs for all these different tools that we were using. So yeah, let me head to my last slide. Thanks, friends. Follow us and stuff. You can go and check out our Twitter, Discord, try a float. You can scan this QR code. Cool stuff.